Hello and welcome to a video on evaluating inverse trigonometric expressions. We're going to work a little bit with the unit circle, and we're also going to be able, by the end of this video, to evaluate inverse trig expressions without using the unit circle. So let's first start off with a brief review of the unit circle. So remember, points on the unit circle are all 1 unit away from the origin. So in my diagram here, that point right there is the origin, and all the points on the edge of the circle are 1 unit away from the origin. So this right here, this is the point 1, 0. It's 1 unit to the right of the origin on the x-axis. 0, 1, that's 1 unit directly above the origin, right on the y-axis. And every other point on the unit circle is 1 unit away from the center, from the origin, which is 0, 0. So points on the unit circle have the important property that the x-coordinate of the point is the cosine of the angle, and the y-coordinate of the point is the sine of the angle. So let's look at an example here. Let's look at this point right here, the point 1/2 comma root 3 over 2. So what this is telling me, there's a lot of information encapsulated in sort of looking at everything that's written down here. So we've got these spokes radiating from the origin. So this spoke right here, it says, I just covered it up, it says 60 degrees equals pi over 3. What that is telling us is that's telling us that this angle made with the x-axis and this segment here, that creates an angle of 60 degrees. So all of the angle measurements here are from standard position, meaning that your initial side is going to be the x-axis, and if you rotate counterclockwise, you'll be using the angle measurement shown. So like if I was over here at 150, that would be starting at the x-axis, rotating 150 degrees counterclockwise, stopping right there. So let's get back to that point in question, this 1/2 comma root 3 over 2. So if I'm looking at this, I can almost think of there being a triangle existing, right, like so. Sorry, my writing is not great. So there's a triangle existing right in quadrant 1, and this is a 60-degree angle. And I could label the sides of this triangle. The hypotenuse is 1, because a point on the edge of the unit circle is 1 unit away from the origin. The y value of the coordinate is root 3 over 2, and the x value of the coordinate is 1/2. So that means from the origin we went over 1/2, up root 3 over 2, and that put us at that point right there. So let's say I wanted to evaluate the sine of pi over 3. So from this triangle I've drawn here, if I look right from the origin, from this vertex right here in my triangle, the opposite side is root 3 over 2, and the hypotenuse is 1. So sine of an angle is the ratio of the opposite side to the hypotenuse. But root 3 over 2 divided by 1 is just root 3 over 2. And you see that's the y-coordinate of the point on the unit circle. So when you're looking at the unit circle, it's great because it easily allows you to determine the sine and the cosine of an angle quickly. If I want to do cosine of pi over 3, that's going to be 1/2. Boom. It's right there. I could also think of it as adjacent. It's 1/2 over hypotenuse. 1/2 divided by 1 is 1/2. So this is awesome because you can just do this so quickly with the unit circle. Like let's say I wanted to know what's the cosine of 3 pi over 2. Well, I just look for 3 pi over 2. It's right here. Cosines the x value of that point. It's going to be 0. What's the sine of 210 degrees? So notice I'm mixing up whether I'm inputting my angle in degrees or radians here. The unit circle has all of these angles that are multiples of, either 30, 60, 45, or 90. They're all listed in degrees or radians. So if I was looking for the sine of 210, I'd find 210 degrees. Notice that positioning makes sense. If I started here on the x-axis and rotated sort of halfway around, I'd be at 180 degrees, but going 210, I need to go a little bit further, 30 degrees more than 180. Puts me right there. What's the sine? It's -1/2. So the unit circle is just, you can see it's just a very powerful tool for evaluating trig functions. But let's look at, I've been doing sine and cosine, but I haven't mentioned tangent yet. But we know that sort of the definition of tangent, I could probably squeeze it right over here, right next to it. The definition of tangent is opposite over adjacent. If you're thinking of points on the unit circle, that would be the y-coordinate over the x-coordinate. So if you're looking from the origin, the y value is always going to correspond to the opposite side of the triangle you draw. The x value would be the adjacent side. So if I wanted to do, say, the tangent of pi over 3, I would just look at the ratio of the y-coordinate to the x-coordinate of y divided by x. Now, both the y-coordinate and the x-coordinate are sort of have a denominator of 2, so that would cancel. So I'm just going to get, here I would get root 3 over 1, which is root 3. So tangent, finding tangent of an angle when you're using the unit circle, I mean assuming it's of a nice special angle, just as easy as finding the sine or the cosine. So I could come over here, we could ask, say, what's the tangent of, I don't know, 5 pi over 6. If we want to do that really fast, we just go to 5 pi over 6. It's going to be 1 over negative root 3. And sometimes you'll see that rationalized if you multiplied the numerator and the denominator by root 3. Sometimes you would see that written as negative root 3 over 3. Great, so now we need to develop some strategies for how we would evaluate trig functions and inverse trig functions if we didn't necessarily have the unit circle. So we need to find a way to sort of compartmentalize all the information contained here in our minds, but we're obviously not going to just memorize every single number on here. That would be a monumental waste of time. We want to develop some strategies for how we can think about all of the relationships and numerical patterns that are prevalent in the unit circle. So let's start with some basic facts that we should know about radians and degree measurements for angles and about side relationships and right triangles. So this is probably the most important relationship, sort of the basic conversion between an angle in radians and degrees that we'll use often is that pi radians is 180 degrees. So from that simple fact, I could take that equation and then quickly come up with some convenient degree to radian conversions that are going to come up a lot, that we're going to see a lot over the course of our study of trigonometry. So if I divided both sides of this equation by 2, I would get that pi over 2 radians is 90 degrees, because if pi radians is 180 degrees, if I cut both of those in half, cutting pi in half would give me pi over 2, cutting 180 in half would give me 90, so pi over 2 radians is 90 degrees. So similarly, I could divide both pi and 180 by 3 to give me the fact that pi over 3 is 60 degrees, and then similarly, pi over 6 will be 30 degrees, pi over 4 will be 45 degrees. So those are sort of relationships that we're going to use all the time. We're going to see those come up again and again and again. So it's a good idea to have a handle on sort of being able to think fluidly about degrees and radians for special angles. Something else that sort of trips up students is that sometimes you'll see ratios rationalized, and other times they might not be rationalized. So just don't lose sight of the fact that 1 divided by root 2 is the same exact number as root 2 over 2. They're the same exact value. They have the same exact decimal expansion. So I mean, if you don't believe me, or if you get confused about two numbers being the same, you can just check on your calculator. You just pick up your calculator, do 1 divided by root 2, see what you get. Do root 2 divided by 2, see what you get. I mean, you could check to see that this is a true statement. If I cross multiplied here, I would get 2 equals 2. That's a true statement. So you need to know this fact, but also be able to convince yourself why that happens to be true. And then the same thing for this, that 1 over root 3 is the same number as root 3 over 3. Those are just sort of two facts that sometimes confuse people. That people sometimes think those are different numbers, that 1 over root 2 and root 2 over 2 are different numbers, when in fact they're not. And similarly, 1 over root 3 is the same number as root 3 over 3. So now let's talk about special triangles. Here I've written down one example of a 45, 45, 90 triangle. Now remember, there's an infinite number of 45, 45, 90 triangles. I could scale this triangle. I could multiply all of the sides by a constant value to produce a new, either bigger or smaller 45, 45, 90 triangle. The angles would stay the same. So notice that root 2, that's what the hypotenuse is for this particular example. Root 2 is it's about 1.41, approximately. That's bigger than the radius of the unit circle. So if I wanted to think about, the 45, 45, 90 triangles, they're embedded within the unit circle. Well, I could divide all my sides by root 2, and I could draw this 45, 45, 90 triangle. Hypotenuse is 1, this is 1 over root 2, and this is 1 over root 2. That is also a 45, 45, 90 triangle. Now, also, here I've got my legs of this triangle are 1 over root 2. I could rationalize that denominator and wind up writing this down for my sides. So, I mean, we're going to use a lot of different convenient 45, 45, 90 triangles. You just need to be able to recognize, that these are both 45, 45, 90 triangles, and the sides sort of follow the same relationship amongst each other. So namely here, if I look at this angle, what's the cosine of 45 degrees? If I'm looking at this 45 degrees, adjacent would be 1 over hypotenuse would be root 2. So if I'm looking at this triangle, the cosine of 45 degrees is 1 over root 2. Now what if I look at this particular 45, 45, 90 triangle? What's the cosine of 45? It would be adjacent root 2 over 2 divided by the hypotenuse, which is 1, but root 2 over 2 divided by 1 is root 2 over 2. But notice, I mean, these are the same thing. Like 1 over root 2 is root 2 over 2. So sort of a way to check to see if you're using a 45, 45, 90, like if you've made a 45, 45, 90 triangle yourself, but you're not sure of the sides. I mean, you know that the cosine of 45 is always going to be root 2 over 2, so you could just check with your particular example. See if it works. So same thing over here. Let's look at, this is one particular example of a 30, 60, 90 triangle. So what if I was evaluating, say, the sine of 30? So let's look at this triangle. What's the sine of 30? It's going to be the ratio of the opposite side to the hypotenuse. So it'll be opposite 1 divided by hypotenuse of 2. And then what if I wanted to look at, say, the sine of 60? Well, that would be root 3 over 2. If I'm looking at the 60-degree angle, opposite's root 3, hypotenuse is 2. Now, let's say I wanted to draw a different 30, 60, 90 triangle, and I wanted my hypotenuse to be 1. So if this hypotenuse was 2, and I want the hypotenuse to be 1 here, that means I'm dividing all of my sides by 2. So I would divide this side by 2, this leg, and divide this leg by 2. Now I can check to see if this all still makes sense, because if I look at my new 30, 60, 90 triangle here, well, the sine of 30 should still be 1/2. Let's check it. Sine of 30 is opposite 1/2 divided by the hypotenuse 1. Yep, the sine of 30 is 1/2 divided by 1, which is 1/2. So you can sort of, the sine of 30 degrees is always going to be 1/2, so I can sort of check to confirm that this is a good 30, 60, 90 triangle. Now why am I spending so much time going through the 30, 60, 90 triangles? It's because when you're thinking of the unit circle, all the triangles on the unit circle have a hypotenuse of 1. So these are sort of the triangles that appear naturally on the unit circle, which are not necessarily the triangles that we might be using, like the exact numbers that we're using all of the time when we think of a 30, 60, 90 or 45, 45, 90. So like if I'm looking at the 60 degree, to go back to my original example here, so I'm looking at a triangle here, boom, there's a triangle, that points on the unit circle, and then what are the sides? This is 1. This is 1/2. This is √3/2, because I know those are the sides because look at the point is right here. From the origin, 1/2 over √3/2 up, and then that point's 1 unit away from the origin. Boom, so that makes, there's my 30, 60, 90 with the sides 1, 1/2, √3/2. Awesome, so just reviewing a lot of stuff here. I know it's a lot of information to take in. So now let's get into sort of the issue at hand, which is evaluating these inverse trig expressions. So the basic rule here is that we're always going to give the angle that's the closest to 0. The closest to 0. And if there's a tie, give a positive angle. So I'll show you what I mean. What if I wanted to do the sine inverse of -√3/2? So what this is saying is this input here, that's the ratio of sides. So I know that I'm looking for an angle such that the sine of that angle is -√3/2. I want to know what that angle is. Now, the issue here is that there's an infinite number of angles that this is true for. But the sine inverse function, it just returns one of those angles. It just returns the one that's the closest to 0. So let's go back and look at the unit circle really quickly. So let's say, I want to erase, so I'm looking at a nice clean unit circle. So I'm looking for a sine value of -√3/2. So I see that here, and I see that here. Those are the two places I see that on the unit circle. So I want to give the smallest angle possible such that the sine of that angle is -√3/2. So let's see, I'm going to write down some statements here. So the sine of 4 pi over 3, that's -√3/2. And the sine of 5 pi over 3 is -√3/2. So let's see here, if I started here and I wanted to get over to the 4 pi over 3, rotating in standard position, I'd have to rotate all the way around here and then stop. Okay, well that's closer to 0, that's a smaller angle than the 5 pi over 3, and then 300 degrees, because that would be if I started here and went all the way around here and then stopped. Okay, so I'm looking for the smallest possible angle, but what if I started here and I rotated this way? Because then I could get to right here, to where I want to go, but only travel that far. So let me erase that up and just draw in that path. So from 0, if I started here and I just went that far, I would get to, I'd create an angle such that the sine of that angle is -√3/2. How big is that angle? That angle is pi over 3. Because look at this right here, this angle right here, that's 30 degrees, and then these two small angles are each 15 degrees. I can see that very easily in quadrant 1. So right here, that's 30 degrees. That's 30. That's 15. That's 15. I know that because this is a 45-degree angle right here. So that's 30. That's 15 to give me 45. Another 15 gives me 60. Another 30 gives me 90, and so on and so on. So you can see sort of that on the unit circle, one of these chunks is 30, and one of the small chunks is 15. So I know that if I start right here in standard position, this is always the starting point, right at 1, 0, and I rotate negative 60 degrees, negative because I'm rotating clockwise, I get to a point where the sine of that angle is negative root 3 over 2. So, and that angle, that negative pi over 3, of my sort of three choices here, that's the angle that's the closest to 0. So that's what we're looking for with inverse trig. We're looking for the angle closest to 0 that produces that ratio. And I guess if there's a tie, get the positive angle. So let's look at an example where there might be a tie. Like what's the cosine inverse of negative root 2 over 2? Okay, so if I look back at the unit, looking for a cosine value of negative root 2 over 2. So that would be here or here. Now it looks like from standard position, that's going to be a tie. That's 135 degrees. If I rotate in the negative direction, that's negative 135 degrees. So I'll just go with the positive angle if there's a tie. So that would be 135 degrees, which would be the same thing as if I said 3 pi over 4, if I wanted to answer in radians instead of degrees. Great, so let's talk about some examples. Let's do this, though, without using the unit circle. So let's say, like, how would I do that? How would I do that last problem if I didn't have the unit circle? So I would need to draw a triangle that produces such that the cosine of the angle is negative root 2 over 2. Okay, great. So now I'm going to start thinking about my coordinates here. Coordinates in the first quadrant are all positive. Coordinates in the second quadrant, the x value is negative, the y value is positive. Coordinates in the third quadrant, both x and y are negative, and in the fourth quadrant, x is positive, y is negative. So cosines, the x value of the point on the unit circle, I want that to be negative. I'm going to go in quadrant 2. Remember, I'm looking for the closest angle to 0. So for cosine inverse, I'm only going to have to look in the top two places. I'm never going to have to look down here. And now I'm going to label up my triangle to match up with these sides. So negative root 2 over 2, well that's actually the same as we'd probably rather think of that as negative 1 over root 2. So if I labeled the sides of my triangle, it'd be 1, 1, and root 2. That's a 45, 45, 90 triangle, so this angle down here is 45 degrees. So now I got to think of how big is this angle, and the two angles have to add up to 180, so this would be 135 degrees. Let's just keep going with the examples here. What if I did the tan inverse of negative root 3 over 3? So the first thing that people might do, I might be like, wait, negative root 3 over 3, I don't like that. I'm going to use -1 over root 3, because usually the triangle works out better when I use the not rational. Okay, so tangent, I need opposite over adjacent y over x to be negative, so I'm not going to be in the first quadrant. I think I'm going to be down here in quadrant 4, where my x value is positive, but the y value is negative. That would make y over x, or opposite over adjacent, negative. And it's going to be close to 0. So tangent's also going to be negative over here in quadrant 2, but that would, my sort of rule for inverse functions is I'm looking for the angle that's closest to 0. So for tan inverse, and for sine inverse, you'll notice as well, you never have to look on that side of the unit circle. So we want to give the angle to be as close to 0 as possible. So now, -1 over root 3, that's my side ratio, opposite over adjacent, y over x. So y over x, hypotenuse would be 2. Boom, there's that nice 30, 60, 90, with the 30-degree angle being here. So what's the angle in standard position? So if this is 30, so my angle in standard position, it'd be -30 degrees rotating from standard position. So this would be -30 degrees. If I wanted to answer in radians, I'd say -pi over 6. So basically it's a lot of triangle drawing. There's a lot of concepts here. This is going to take a lot of practice to get good at. It is not at all easy. You can confirm this with your calculator. So here I'm doing the tan inverse of -√3 over 3, which is the example that I started with here. I changed it to -1 over root 3, but I started with it being the tan inverse of -√3 over 3. So notice I do that on the calculator, and notice this answer comes back, -0.523. Like, what's going on with that? But remember, the calculator, when it gives you an answer in an angle in radians, is not in terms of pi. So if we check that out, like, that is -pi over 6. I did -pi over 6 on the calculator, the same decimal expansion. So that confirms what I just did, that the tan inverse of -1 over root 3 is -pi over 6. Like, that matches up with my answer right there. And if I change my mode, if I go into mode and go into degree mode, and then redo the tan inverse of -√3 over 3, notice how it doesn't give me the answer of -pi over 6, it gives me the answer of -30 degrees. So when you're doing an inverse function, whether your answer comes back in radians or degrees is going to depend on what mode you're in. And Wolfram alpha is also a really good resource to check here. I could type in the tan inverse of root 3 over 3. Notice I type this in as arc tan of -√3 over 3. And this has come up in a bunch of the Khan Academy videos, and I think we've talked about this before, but like arc tan, that's the same thing as the tan inverse function. So I just wanted to type it in that way to remind you. Arc tan, the same thing as tan inverse. Arc sine is the sine inverse function. Arc cosine inverse function, so on and so on. So Wolfram alpha is great because it gives you this input box. So that, what Wolfram alpha puts in here, that is the interpretation of what you've typed in. So I typed in arctan parentheses -SQRT because I don't have a square root key on my keyboard, so I have to know the abbreviation for square root. Wolfram alpha is SQRT. Make sure I got all the parentheses right. So then Wolfram alpha is saying, did you mean the tan inverse of -√3 over 3? Yep, that's exactly what I meant. And then look at this. It gives me the answer in radians. It gives me the answer in degrees, and it gives the decimal approximation of what -pi over 6 would be. It gives me the decimal expansion out to very many decimal places. So, again, these are very difficult concepts. This is going to take a lot of practice to master, but we're going to be working on this for a while in class, so good luck.